Hello everyone, I am Dr. Clement, Research Assistant Professor, Department of Chemistry, SRM Institute of Science and Technology, KTR campus. Today, I'll discuss a module of theory of indicators. This concept is one of the most interesting concepts in analytical chemistry. So in this module, today I'll explain the theory of indicators. So here, most of the acid-base indicators are very weak organic acid or bases. Let me repeat this. Most of the acid-base indicators are weak organic acid or base. Oswald suggested the first theory to explain how an acid-base indicator works. Let us consider an indicator which is a weak organic acid represented as HIN. H means proton, IN means indicator. So let us consider this as case 1. In this case 1, we assume that the indicator is weak organic acid. Now let us try to understand how it works in aqueous solution. If we take this weak organic acid and drop in an aqueous solution, it will dissociate as follows. This HIN, which is in the undissociated form, is in different color, whereas upon dissociation it renders or it produces H plus ion plus indicator minus. This is in dissociated form. This dissociated form renders a different color, meaning that the undissociated form shows a different color while the dissociated form shows a different color. So that is the basic aspect of indicator. The undissociated molecule of indicator, weak organic acid indicator, has one color while the color of HN minus is different, as I said. If this indicator is placed in a solution of acid for the sake of titration, then the following equilibria will exist. That is, the undissociated weak organic acid will dissociate to give H plus ion plus indicator minus. Note it carefully, since we dropped in an acid, this acid also dissociates to give H plus ion plus the anion. Note that there is a common ion. Both of them renders H plus ion, the indicator as well as the solution. Therefore, this common ion induces a common ion effect, the so-called common ion effect. Therefore, due to the common ion effect, the dissociation of HIN, that is the weak organic acid, is already poor because it is a weak acid. The dissociation is further decreased as shown by the arrow at the top. Thus, the presence of an acid, the concentration of H plus ion, the concentration of IN minus ion becomes very small, and most of the indicator will be in the undissociated form. So the color shown will be that of undissociated form. So the color also will be in the undissociated form. If the indicator is added, say for example, if the indicator is added into a solution of alkali instead of acid, if it is added into the alkali, then the dissociation of HIN will increase as shown below. See, look at here, this HIN renders H plus plus IN minus. This MOH gives OH minus plus M plus ion. Here look at this. the indicator dissociates H plus ion and the alkali, which is the base, which gives hydroxyl ion. So these two will join together and give water molecules. Because of this, we will get more dissociated indicator ion, which will show a predominant color. See, look at this. This H pH renders H plus pH, which is pink. pH means here phenolphthalein indicator. This is an example. Let us take a phenolphthalein indicator, and which gives H plus ion plus pH minus ion, which is poorly dissociated. So in acid solution, due to the common ion effect, the dissociation of the indicator is suppressed. So most of it is present in the undissociated form. Consequently, the solution remains colorless. In alkali medium, the hydroxyl ion combined with H plus ions form an indicator to form water. This pushes the dissociation in forward direction. Therefore, the concentration of pH minus ion increases and hence the solution becomes pink. Let us now consider an indicator that is a weak organic base, that is case 2. In case 1, we have seen weak organic acid. If you just pour that in an acid, due to the common ion effect, there is no much dissociation, so the color will appear in the undissociated forms color. While the same organic acid, if you just put it in base, there will be, the base will render OH minus ion, so that it will join with the H plus ion which comes from the indicator, and it will give you water molecule, so that there is more dissociation and it will give you more dissociated color. And for that, we took phenolphthalein as an example, and phenolphthalein gives H plus and the dissociated pH minus gives pink color. This is how pink color appears. Whereas in the case 2, we are going to take a weak organic base. The indicator will dissociate as follows. This is an indicator and which has OH minus ion, which is the undissociated color. The dissociated will give indicator ion plus OH minus ion. This is also a weak basic indicator, no, so poorly dissociated. In alkaline solution, the concentration of the common ion, that is OH minus, will be high. The already poor dissociation of weak organic base will be further decreased. So most of the indicator will remain undissociated and the solution will have the undissociated color. Whereas in acid solution, the hydroxyl ion from indicator will combine with the H plus ion from the acid. This would push the equilibrium in the forward direction. The concentration of indicator plus ion will therefore become greater and that of the indicator, so that the dissociated color will be exhibited. For example, let us take methyl orange, that is MEOH, is a weak organic base, which dissociates as follows. This MEOH will give Me plus OH minus. This is methyl ions, positive ions, and this is hydroxyl ion, which is poorly dissociated. In the presence of alkali, the equilibrium will exist as follows. So this is the methyl orange. As you know, the methyl orange, this will render the hydroxyl ion. This is the methyl orange cationic part, and this is the basic solution, which gives also a hydroxyl ion, and this is the positive counterpart. So this is at a common ion. Since because of the common ion effect, the equilibrium will shift towards the left hand side. So the indicator will not dissociate much. It will remain undissociated. The color what we see is undissociated color. Now let us see. This will say, for example, if the same thing, if we take in acidic, same methyl orange in acidic medium. So this methyl orange will give Me plus hydroxyl ion. This acid will give anionic part plus H plus. See here, there is no common ion. Since there is no common ion, this will form a water molecule. Therefore, the dissociation of MEOH will become much greater. Hence, the concentration of Me plus ion will be greater than that of MEOH, so that the solution will turn red. That is called the dissociated color. So this is how theory of indicator works. So in case 1, we have taken weak organic acid. In case 2, we have taken weak organic base. And for the former case, we took phenolphthalein as an example, and in the later case, we took methyl orange as an example. Now let us try to understand the change in the pH during the titration of organic acid with a strong base. How the pH changes, that's called effect of pH basically. How the pH changes during the titration of organic acid. Let us calculate pH at different stages of titration of 50 ml of 0.1 normal HCl with 0.1 normal sodium hydroxide solution. The pH before any NaOH added, that is 0.1 normal HCl. I mean, like before any HCl means we'll have only one. In the conical flask, we'll be only having 0.1 normal HCl. So what is H plus? H plus is equal to 0.1 gram ion per liter. That is 10 to the power minus 1 gram per liter. So what is the formula for pH? Let us take a logarithmic equations. Log H plus is equal to log 10 to the power minus 1. That is equal to minus 1. So take the negative multiplication on both sides. So negative logarithm of H plus is equal to negative logarithm of minus 1. So minus 1 into minus 1 plus 1. So the pH is 1. Now what we understand is pH before any NaOH is added is 1, which is highly acidic in nature. Now we will calculate what is the pH after the addition of 10 ml of NaOH. See, in the first case we did not add any NaOH, whereas in the second case we are going to add 10 ml of NaOH. In the first case, since there is no NaOH addition, so we did not consider NaOH at all. Only 0.1 normal NaOH. For that we calculated what is the pH. That's it. Correct, no? In the case of like 40 ml of addition of 10 ml of NaOH. Now if we add 10 ml of NaOH, 40 ml of acid is left, because for 10 ml of NaOH, 10 ml of acid would react. Correct, no? Because we took 50 ml of acid. So the remaining 40 ml of HCl is left unreacted. So the total volume became 60 ml. So in this case, the normality of HCl can be calculated. That is normality. That is V1 N1 is equal to V2 N2. That is 60 ml V1, and N1 is what is the normality of that is equal to V2 is equal to our 40 ml, and N2 is equal to 0.1. So therefore the normality is equal to 40 into 0.1 divided by 60. That gives 0.06. Now we calculated what is the normality of HCl. That is 0.06. The formula is simple. The same V1 N1 is equal to V2 N2 formula. So it means now 0.0667 gram equivalent gram of HCl are present per liter. That is H plus ion concentration is equal to 0.066 gram per liter. So what is pH? The formula pH is equal to negative logarithm of H plus. That is equal to negative logarithm of 0.0667. So the negative logarithm of 0.0666 gives you the pH value around 1.8. It's very interesting to note, after the addition of a 10 ml of NaOH, the pH is slightly increased from 1 to 1.18. Now, hence, when the titration is 20% complete, the pH rises from 1 to 1.8 is the conclusion. Now, let us go to the case 3. pH after the addition of 20 ml of NaOH. So, H plus N will be given as 0.1 multiplied by 30 divided by 70. Why 30 here? Because 20 ml of NaOH consumes 20 ml of HCl. So out of 50 ml of HCl, how much HCl is remains? 30 ml. And what is the total volume? 70. That is why 0.1 times of 30 divided by 70. That gives 0.0428 gram per liter. So what is the formula for pH? pH is equal to negative logarithm of H plus ion. That is pH is equal to negative logarithm of 0.0428. Now if you calculate the pH, now the pH is going to be 1.37. It's very interesting to note. Now the pH is again raised to 1.37. So initially the pH was 1 without any addition of NaOH. After adding 10 ml of NaOH, the pH raised from 1 to 1.8. After the addition of 20 ml of NaOH, the pH increased from 1.18 to 1.37. Now let us assume case 4, that is pH after the addition of 50 ml of NaOH. Now you all wonder, because we have 50 ml of HCl and we are going to add 50 ml of NaOH. There is complete neutralization. So at this stage of titration, the reaction is just complete. That is, the equivalent point is reached. The titration mixture is now merely the solution of NaCl in water, and because of Na plus and Cl minus ions do not hydrolyze, the solution is neutral with a pH of 7. Now, pH after the addition of 50.1 ml of NaOH, what happens? Like now everything is completed. Now we are adding additional, right? I mean, like additional NaOH we are adding. See, out of 50.1 ml of NaOH added, 50 ml is used in completely neutralizing the acid, and 0.1 ml is present in excess. Just 0.1 ml of NaOH is present in excess. Now, the total volume of the reaction mixture is 100 ml, or approximately 100.1 ml. In other words, 0.1 ml of 0.1 ml of NaOH has been diluted to 100 ml in the solutions. The normality of NaOH can be calculated, that is, because we cannot calculate the normality of HCl, because HCl is no more there in the solution. So that is why we can calculate only the normality of NaOH. That is, normality of NaOH is equal to 0.1 multiplied by 0.1 divided by the total volume is 100, which gives the normality 10 to the power minus 4 n. Now let us carefully understand. Now we cannot calculate the pH directly. Now we need to calculate how much H plus is left. So for that, we all should know concentration of H plus is equal to 10 to the power minus 4. That is, we can express like this. That is, concentration of H plus multiplied by concentration of OH minus is equal to 10 to the power minus 14. This is the conventional equations. Therefore, the concentration of H plus is equal to 10 to the power minus 14 divided by the concentration of OH minus ion. That is nothing but 10 to the power minus 14 divided by concentration of OH minus ion is nothing but 10 to the power minus 4. That is nothing but 10 to the power minus 14 multiplied by 10 to the power minus 4. That is 10 to the power minus 10 gram ion per liter. Therefore, the concentration of the solution is 10 to the power minus 10. Hence, the pH of the solution will be 10. Yeah, this is the final table by which we can clearly understand the effect of pH. Therefore, just by look at it, when we add 0 ml, the pH is 1. If you add 10 ml, the pH is 1.18. If you add 20 ml, the pH is going to be 1.37. If you add 30 ml in NaOH, the pH is going to be 1.60. If you add 40 ml, it is going to be 1.96. If you add 49 ml, it is going to be 3. If you add 49.9 ml, the pH will be 4. If you add 50 ml, the pH is 7. Now the interesting thing, if you add 50.1 ml, then the pH is going to be 10. See, drastically increased. That 0.1 ml of NaOH increases the pH from 7 to 10, all the way from neutral pH to completely a basic pH. That is the interesting aspect of this acid-base titration. That is why we need to very carefully do the titrations, because even 0.1 ml makes a drastic change in the pH. And now imagine if you add 51 ml, then the pH is going to be 11. If you add 55 ml, then the pH is going to be 11.68. And if you add 60 ml of NaOH, excess NaOH, then the pH is going to be 11.96. That is close to 12. So therefore, the conclusion is, even a 0.1 ml of excess NaOH changes the pH dramatically from neutral to alkaline. So that is the effect of pH during the titration of acid base. And the conclusion is, when we do such acid base titrations, we have to be very careful when we add or when we titrate with the NaOH solutions. So with this, I'll wind up this module.